Yes, sir.
Okay,
Yes,
okay.
sir. That's from the test.
Okay, so which problem number was this?
So question number 3, sir.
Uh, F, yes. Can you say the question?
Yes, sir. So f of x1, x2, x3.
Uh-huh.
It's a polynomial, multivariable polynomial with integer coefficients.
Right.
Yes, sir.
Hmm.
And it's given that f of pi comma 1 comma 2 is 0.
Okay.
So now we have to prove that f is 0 at infinitely many points.
F is 0 at infinitely. Right. So how did you do this? I think you had done this one, but I don't know if it's correct. Don't remember.
Yes, what I did was I split it into 3 polynomials. One polynomial in x1,
Mm-hmm.
one polynomial in x2, and one polynomial in x3. So I wrote f of x1 comma x2 comma x3 is equal to p of x1 plus q of x2 plus r of x3.
Okay, okay. So do you think that can always be done?
Now I realize that it can't be done, so because we can have x1, x2, 4x2, x3 and stuff like that.
Yeah, you cannot separate. So that's the thing.
Yeah, you can't separate it like that.
You can't separate it like that. Right.
Yes, sir. So what would we do here, sir? From like when you look at it, it looks like you have to use that pi is transcendental or something like that.
Yes, yeah. Pi is transcendental, you would have to use. So what do you mean? What is the meaning of pi is transcendental?
So it
Would-
means that pi is not a root of a polynomial with algebraic. I'm sorry, what is that? Integer quotients.
Yes, right. And even algebraic coefficients is correct, but we just need
Yes,
to
sir.
use that
Uh, integer.
integer coefficients, right?
Yes, sir.
So how do you use that? So see, the point is that the statement you're making, pi is not the root of a polynomial with integer coefficients, that is a statement in one variable,
Yes, sir.
right?
In one variable.
So we need to reduce this problem to one variable case
Yeah. Yes, sir.
somehow. So the natural one variable case to consider is just take this. Consider this polynomial,
Okay.
or
Yes, sir.
rather, this is wrong notation. I would, yeah, yeah, but you know what I mean. Is just take this polynomial.
Yes, sir.
Now you try to think.
So, sir, if we have that p of x1 is equal to f of x1, comma 1, comma 2, and then we know that all of these here are integer coefficients, but still p of pi is 0.
Hmm. P of pi is 0, right?
So p of x must be the 0 polynomial.
Yes, that is it actually, right?
Yes.
Yeah, you just
Yes,
write
sir.
that P of x1 is also in integer coefficients, and P
Yes,
of
sir.
pi is 0, and so it must be 0 polynomial, right?
And then same argument. So since here it is 0 here, it will be any x1 you put, it will be 0.
For f, yes. So you have to just
Yes, sir.
write. So we are in fact getting that um, we are in fact getting that all these are roots.
Yes, sir. All x where x1 belongs to R.
Yes. So in fact, it is not just infinitely many. It's like a whole of R kind of, right?
Yes, a whole
Uh,
of R.
in some sense, yeah. So yeah, it's a very easy question. There is yeah.
It's an easy question. What I was looking for is one that doesn't use this algebraic and what
Oh,
transcendental
no, no. I
concept.
I don't think you, because otherwise, how do you define pi?
Yes, otherwise, yeah. So
There is
I
no.
spent some time on that, but then I didn't find any. And then I realized that, yeah, you'll have to use this sorry. algebraic,
Transcendental.
non-algebraic. Yes,
Yes,
sir.
because proving that pi is irrational is not easy. That is probably,
Ye-
I think, equally hard as proving that it's transcendental, kind of.
Yes, sir. Yes.
So,
Yes, sir.
okay. So let's see if there are other questions.
Yes, sir. Sir, there was one sixth problem, sir.
Hmm.
Prove that n factorial is greater than or equal to n by e to the power n. Yes.
Hmm.
So when I looked at it, I thought induction or something, but still I don't know how to do it, sir.
Induction does not work. Yeah, because
Yeah, sir.
this will become n plus 1. Hmm. So there is a kind of a formula for this, but that if you use it in a subjective, you will probably not get marks unless you prove it. And that is the
Yes, sir.
Stirling approximation.
Sterling, okay.
Yeah,
Yeah.
but
Now
we will
that
not.
you say it, it was.
Yes, you can use it in MCQs, but we will not use this because we will not. That's unless you prove it, and proving that is probably harder than proving this thing.
Yes, sir.
So yeah, let's think about how to prove this.
So is that n factorial is approximately equal to root 2 pi e power? Sir, that one, no, sir.
Yes, yeah. What is the formula? Root 2
I
pi.
think some square root 2 pi will come, sir. Yes, sir. Something like that. And then e power. Yeah.
Yeah,
Yes,
so
sir.
it is precise. It is like this. This is like a special case of this, right?
Special case. Yes, sir.
Right, because then n factorial will certainly be bigger than this. So
Yeah. Yeah, but otherwise, how would you do it, sir?
yes, so there should be a way. Let's see. So we might. Induction does not work. If you look at log 1 that's 0, but log 2 plus log 3.
Yes, sir.
So just taking log on both sides.
Okay, so
Like
if you take log on.
uh, so I'm just trying to convert it to a summation.
Yes, sir.
That's the only thing. And then I may use some summation technique. So this is like a product thing, but it's easily convertible to summation because of the log thing that we have.
Yes, sir. So if you take the log of the right hand side, you'll
Mhm.
get n log n by e. Log a by b is log n minus log e.
Yes, you can
So
do
that'll
that.
be, it looks a bit like the integral, so integration of log x. So maybe something like that.
Yes, exactly. That's a good idea. That's it's what I was. Hmm.
Yes, sir.
Yeah, so we can apply. We can try to apply some kind of integration.
Yes,
Uh,
sir.
hmm. But okay, so we will come to integration. But right now, another idea strikes me, which I'll try to apply first. Because integration,
Yes,
this
sir.
problem can be done by that. I am
Okay, sir.
pretty, it seems pretty sure. But I am thinking of some inequalities. Okay, uh,
Yes, sir.
let us see if that works. I may not work, but so do you? Let's just look at the graph, and then it will be clear. This thing, and then let us say that there are 2 points A here and B.
Yes, sir.
Then you take log A plus log b. Now, if I ask you to compare this with log a plus b by 2, which is here,
Yeah, so in the middle.
right? I mean, this by 2 comparing. So which one is bigger?
Uh, log a plus log b by 2. We have to compare with log a plus b by 2, sir.
Yes. Yeah, but I think this is
So,
bigger.
yes, sir. Yes,
Yes,
sir.
because it will be, yeah, because, yeah, is that clear? So this is log a height, just comparing the
Yes, sir.
heights, and this log b, and then the average height will be on the line, but it will be here. So this
Yes, sir.
quantity is here. So then
It
this formula
always
doesn't
lies
work.
below.
Yes,
So,
yeah.
is
So
this Jensen's
this is
inequality?
Jensen's, yes, it's very special case of the
Okay.
Jensen's inequality, right? And
Yes, sir.
yeah, obviously these things you could check formally by taking second derivative, but I'm not going
Yeah.
into all that.
Yes.
Uh, yes,
Yes,
but
sir.
so it doesn't seem to work in this case because we needed the reverse,
Okay. Oh,
right? I think, yeah, we needed the reverse, so it doesn't.
yes, sir.
So it's less, but still, if I try to make it work, let's see. So if I write it like this, so this is correct. I mean, this is equivalent to this.
Uh, so you log 1 remains the same. What is this? A 1.5 log 1 by 3. Yeah, yeah, yeah.
Yeah, so
These are
just
all smaller.
yeah, means this is negative of
Yeah.
this, right? So it switches,
Yeah,
sign switch.
negative, negative.
This side also
Yes.
switches. So I've just done that because I want to
Okay,
apply
yes, sir.
that thing. This, you understand, naturally.
Yes.
Yeah.
Yes, sir. Yes, sir. Got it.
So now if we apply Jensen, I think it will not work because the quantities are varying a lot. But if it works, then
Correct,
it
sir.
works. Means that these inputs are varying a lot, right? So the
Yes,
averaging
sir.
is not good if the quantities are like very scattered. But let us see. I
Okay.
mean, so much I cannot say from before. So just apply this. So by Jensen's inequality, if you can forget this for a second, and by Jensen's inequality, this is less
Yes.
than 1 plus this by
Over
n
n.
over n.
Yes, sir.
Yes, right. Now you just want to show that this is less than this.
Okay, so we have to we can remove the log,
Yeah,
compare what's in the
yes,
parentheses.
but that is not true. I
It's
mean,
not true.
yeah, so my method will not work is what I'm saying. This is not correct.
Yeah, yeah, it'll eventually get bigger.
It will get, yes, exactly. It will get bigger and bigger.
Yes.
So we learn a lesson, that's all, that this does not work.
It doesn't work.
It
Yes.
seemed like it will not work because the quantities, they don't have a sort of a symmetry. So yeah, anyways,
Yes, sir.
but like if it was like, so it would have worked if it was like 2 square, 3 square, then it would have worked, right?
Yeah.
Some
Yes, sir.
things like that. Some with some changes, this may work. Well, let's roll back. This does not work. Okay, now integration.
Yes, sir.
So so what does integration tell you? What can you do?
Sir, actually, the limit integration as a limit of sums, I
Hmm.
still haven't done that yet, sir. So I don't fully know how it works.
Okay, that's right. Okay, but I uh, minute.
Yes.
Yes. So, okay, let me then say what is integration as a sum. Then you will know better whether you can apply it here or not. So
Yes, sir.
the whole point is very simple, that you just have this sum curve, and
Yes.
let's say from A to B, and you want to find the area, or you want to have a sensible notion of area. Then we
Yes, sir.
approximate the area with rectangles, and we take A plus. So let's say you divide it into n parts.
Yes, sir.
Let's say n equal parts. So your thing will be like k by n, the arbitrary point here in the partition
Yes, sir.
is like k by n, and then what do you do? So basically we take the area of each of the strips, and the area of each of the
Okay, sir.
strips uh, is 1 by n is the base length, and
1 by n. Yes, sir. That
that's
many.
going to be
Yes, sir.
the
Yes.
base length, because that's how I'm taking the partition, a plus 1 by n, a plus 2 by n. So
Okay,
1
sir.
by n is the base length, and the height is, you can take it to be anything in between. Let's say you're from a to a plus 1 by n, then what should you
Yes,
take as
sir.
the height, right? So there are things, but it's approximately, you can take it to be anything, because we assume that there the
Okay.
function is not changing much and so on. So we can just take it to be a, let's say. Yeah, I mean a
Yes,
meaning,
sir.
okay, so you can't always take it to be a. What I mean is that you can take it to be a
F of
plus,
n.
yes, it's right, f of a plus k minus 1 by n.
Yes,
So
sir.
you take the left hand point, and then you add
Okay.
this,
Okay. Yes.
right? You add this where k goes from 1 up to, so you just to go to a certain point till you reach this b, right?
Yes, sir.
Yeah. So that's
Correct. Yes,
yeah.
sir.
So this is how the Riemann sum will look like.
And then when you take the limit as n goes to infinity, it turns into the definite integrals between a to b.
Yes, we define that. That's a definition of the definite integral.
Okay.
Okay,
Yes,
when
sir.
you take the limit, that's a definition of the definite integral. So this is
Okay,
the
sir.
story. Now, but the point is that you need to see this thing as some summation like this. So how do you see that?
Hmm. So one problem I see is that the quotients are all 1 instead of that 1 over n.
Yes, yeah. So that we can adjust by bringing this n this side.
Huh. Okay, okay. Correct, correct. Correct.
So these are the base lengths. And now how do we adjust the heights?
Law.
Also notice one thing, that we have to prove this for every n, and this thing is kind of this, like this limit, this summation, you can use
Yes, sir.
integration only in the limit. Only when you take the limit n to n tend to infinity, that you can say that it is integral from this a to b, and only then you will have a chance to use the integral, some formulas of integral.
Okay.
You see the point, right? So when you want to prove something for, because first thing is that means what's the advantage you want to take? We want to take the advantage of this integration, right?
Yes,
That
sir.
this integration
Integration.
has other ways to compute the integration by antiderivative and so on. So integration is like magical, because there are like two ways we define it. One is area and
Yes,
one is
sir.
antiderivative, and they don't seem to have any connection, but yet they have, right? So
Yes, sir.
you have this summation, and but only when you take the limit is this summation equal to the integral, and
Okay.
then you can take the
So,
advantage of the integral. If you don't have, if you're not going to limit tend to infinity, then how are we going to use it? That is the question, right?
yes.
Right. So that's why I don't think using it in this way will be very useful. Okay, yeah, but
Hmm.
still
Yes, sir.
we can actually take a much easier interpretation of integration and try to do this. So there is another, uh, we'll see. So this, so what did I have in mind here is the following. Like you suppose we take, so we are taking log 1 onwards. So
Yes, sir.
let's say we are taking a curve like this. This is roughly how it is, right? So
Yes, sir.
then you go, let's say, all the way till n. Now, so this summation, we try to interpret this in terms of area. This summation
Okay.
itself, this finite summation, not in limit and so on, this finite summation itself, we want to interpret in terms of areas. So how do we do?
Okay, sir.
So let's say that you have log 2. So, so you have 2 and this height is log 2,
Correct. Yes, sir.
right? This height is log 2. So this area of this rectangle is log 2,
Yeah, log 2.
right?
Right. Yes, sir.
Yeah. So because this function, this graph is x comma log x, that's what the points are. So now similarly, when
Yes.
you take 3, right?
Area will be log 3.
Yes. So now you get that this thing, this area, you know what this is coming. So this would
Yes,
be
sir.
log n, right? Now you can see directly from the figure, while writing you have to maybe write a few things, but directly from the figure that this should be bigger than, what can you say in terms of integral about this?
In terms of the definite integral from A to B.
Yeah. Yes, yes.
Sorry, 1 to n. So 1 to n.
1 to n, yeah, same thing. Yes.
Yes,
So
sir.
not same thing, yeah, 1 to n.
Yes, sir. Because we can see that the overflow area, I mean, we have extra area instead of less area. So we can say that this finite sum is bigger than the definite integral of log x dx from 1 to n.
Yes. Now we
Okay.
can try. I think now the problem is done because you already know the
Let's,
formulas, right? It's x log
yes,
x,
sir.
n to 1, and you put the values, and this is exactly what you saw first.
Yes, sir. Yes, sir.
Done.
Okay.
This
Yeah,
technique
yeah.
is, so this technique is nothing, is not some very difficult thing, right? It's very straightforward thing.
It's straightforward, sir. Yes, sir. We
Yeah.
all the we had to graph it first to see the
Yes.
thing.
Yeah. There is this idea that each number there is representing an area. Means you have to see it as an area of something, right?
Yes, sir.
Which is what we
Yes.
usually don't do, right? This thing, you see it as an area of this rectangle is the idea. Okay. So
Yes,
this
sir.
goes under the topic of approximating summations with integrals. Okay.
Okay. Yes, sir.
You can, yeah, you can see it online. There are many other variants and things about these things. And this formula I have seen used in many CMI questions. 2 CMI questions I can remember, kind of. I don't know
This
which year.
integration.
This particular thing, interpreting this summation as an integral.
Oh,
Maybe there was a
okay.
decreasing
Yes.
function, or you have to. So sometimes you may have to under approximate. Like this is also log 2. Okay.
Yes,
This is
sir.
also log 3. Then you may have to take integral till n plus 1. But then you'll get that this
Correct.
is
Yes.
less than that. So this is a very nice formula because this helps you to say that this is greater than some integral and it is also less than some integral. So it will be less than integral from 2 to n plus 1 log x dx. Similar
Yes, sir.
idea.
Less than n.
Yes, it's a very because so it has this sandwiching capability which may come into play
Yes, sir.
if you have to prove some limits. Yeah. So it's
So
a
we
very
can
nice
see that this sum, it's always sandwiched between the
two
n plus
integrals.
1 integral and the n integral. Yes, sir.
Yes, and this can have many consequences. Also, you can see that the error. So even if you go to the first basic approximation that we did, uh,
Yes,
what
sir.
is the error? So meaning what I mean is that
It's
what is the difference?
quite a bit, sir. It's not a small error. So
Let's see. So let's see how much is it. Uh, no, so it is, no, yeah, you're right. I mean, it is there, but so like the difference is, how should I say? No, but the error, so okay, can you see that the error is less than log n?
less than log n, sir.
Yes. In fact, it is it is less than log n by 2.
Sure, I don't know how you. So, if the error we are interested in is the area of the rectangle that. So, not the
Yes.
rectangle. This
Let
above
me.
curve
Yes.
less than log n by 2. So, I don't know how you got that, sir.
Yes, yeah. So you can do it by, if you upper approximate also, then you can take the difference between the upper and the lower approximates and you will get the answer. Because those two are
Oh,
simple quantities. But I am seeing it, trying to see it a little geometrically, that you see, it's like you have this. Suppose that this is the error, though it is not. Let's say this is the
yes,
error.
sir.
So this is more than the error. And then you take this thing and you stack it here.
Oh, okay,
And
like
then you
that.
understand. Yeah. You take this thing and you push it here. But you see, the heights never grow more than log n.
Yeah, yeah.
And
And
so
then
the,
this thing that we're counting, it's in fact more than the error. So, the
yes, yeah, it's in fact
error.
more than half of the error.
Yes,
Again, that
sir.
is because of the convexity of the curve, right?
Huh.
You
Right,
can
yes, sir.
understand it. So all that you should obviously write down, but this is actually a good approximation in that sense.
Yes, sir.
Yeah,
Is it-
I just, let me just see this Stirling's approximation. I think it is also proved by this kind of idea only. I'll
Oh,
just, yeah, then you can actually try to prove that for homework. So Stirling's approximation is seen as something, okay, not in the syllabus, but actually I think it's easy to prove.
yes, sir. Sir, and one more thing.
Huh.
When we actually do the integral, we'll get that the entire summation is greater than n log n minus n plus 1. So that plus 1, here what we get, so we get the answer, but then we get that it's a strict inequality, sir.
You mean here you will get it strict?
Yes, sir.
Uh, right, okay, so you will end up proving this, but that's okay,
Yes,
right?
sir, we'll end up.
But that is
Yes, sir.
okay,
Yes.
because this implies that it is greater than or equal to.
Yes, sir.
Because yeah, it is contained in that. So no, but let me see the Stirling's approximation, because from what we have discussed, I think it can be done. I mean, we can try to do it, but because of the time, we just see if uh, the proof. So this is the formula, and you see, this is really what it is. You have to convert it to log, and then you have to. That's one way
Yes,
to
sir.
prove it. That will not be the only way. Yes, so you can see that
With an integral. Yes, sir. This
it
is
is the
what we were
same
talking
kind
about.
of thing. Okay, yeah. Maybe at some point they will.
It's-
No, so this one is fine. Hold on. There are other proofs, gamma function, but okay, wait. Let's just go over it since we are. I mean, so
Yes, sir. So
yeah.
log n factorial is the summation of. Yes, sir.
Mhm.
Then they're
So
approximating that with the integral, what we just took.
yes, and this integral is this thing.
That's what n log n minus n plus 1. Yes, sir.
Yes, that's right. Now the full formula together with precise estimates of its error can be derived as follows. Instead of approximating n factorial, one considers its natural logarithm.
The right hand side of this equation minus. Okay. So they're taking log n factorial minus half log n.
Yes, and that
And
half
this,
log.
so the half log n is the error that we
Yes,
got.
that's exactly. Yeah,
So
right.
they're making it more accurate.
Yes, so they're making it more accurate, and that is roughly equal to that, and that is equal to that.
Yes.
But then at some point they are using some other formula. Uh, so this thing is equal to this thing, that is just by definition, that is equal to this plus this. Now I don't know how that comes. So dk is a Bernoulli number. Take limits. get this. No, this goes a little deeper. But
Yes, sir.
but once we had done a proof in college and it was not difficult. Anyways, I think
Okay.
about yeah. So but the pi will come in some way. The pi has to come somehow. And
Yes, sir. The pi
yeah,
has to come.
yes. But still, we have a nice approximation, and it's actually good enough for a lot of purposes. This formula,
Yes, sir. This
yeah,
n log and this integral 1
yes,
to n.
yes. And this
That
formula itself,
along with the n
is
plus
quite
1.
nice. Yeah.
Yes, sir.
Because you see, if
Yes,
you
sir.
do the upper approximation, you also get that something like in this or something like this, something, right?
Yes, sir.
So this itself
Right,
is a
right,
good
right. Yes.
approximation. So yeah.
So then we can probably use this question in limit or something.
Yes,
Sandwich
yeah.
theorem.
Yes, sandwich theorem, or if you have a question with n factorial, then you can use this inequality because you can prove it
Yes,
very
sir.
easily. Yeah. So it's a
Yes.
simple version of Stirling's formula, but it is just good enough for a lot of things, I suppose.
Yes, sir.
Okay. So so do you have more questions? The first question I'm not discussing because it's easy. Just give it a try again. Means that
Yes, sir. I forgot what it was actually, sir. I haven't. Oh, the
quadratic
floor
one.
function one. No, 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 sir. The
The
floor
floor function.
function.
I don't know about that question actually. I don't know if it's easy or not.
Yes, sir.
Yeah.
I
So
tried,
should
sir. I
we?
tried.
Yeah. Okay. So then what should we do? Which question should we do now?
So what I was thinking was, I began by solving, what my friend and I, like we're
Hmm?
both solving CMI papers, same paper, and we're comparing our scores. So we started with CMI 2010 paper. So I did pretty well. I got 76 as my final score. So
Okay.
now I was thinking, maybe we can solve CMI 2011 part A. We can do, I think, more than half of part A in the time that we have now.
Yes. Yeah. So we can do that. Yeah. So let's just
Yes.
relaunch the meeting, and we'll discuss. Okay.
Okay, yes.
Yeah.
So I'll leave and I'll
Yes.
rejoin
Yes.
this